Good afternoon and welcome to this webinar, Commercial GeoExchange System Designs. This event is brought to you by the news and is sponsored by Climate Master. I'm your moderator, Mike Murphy, Editor-in-Chief of the news, and thanks for joining us today. So let's get started. Today's expert presenter is Trey Austin. Mr. Austin is the President and CEO at GeoEnergy Services and a consultant for Climate Master Incorporated. He is a certified energy manager, a certified GeoExchange designer, and a lead AP. His expertise focuses on energy analysis and optimization of HVAC design, operation, and commissioning, and integrating technology-specific solutions. He has 16 years of experience with research, design, and consulting for ground source heat pump systems. Experience with GeoExchange systems ranges from residential to large-scale commercial projects across the United States and internationally. Now, before we begin the presentation, I want to provide you with a few housekeeping items. To the left of the slide area, you will find a resource box. This allows you to click Help for technical difficulties, enlarge slides for better viewing, or download slides for a printable copy of today's presentation. You can even invite a friend to join us if you like. If you need any additional assistance during the program, you can email us at webinars@bnpmedia.com. Above the resource box, there is a blank questions box that allows you to type a question in the box and then hit Submit Question. That will send it to us. Later in the live program, Trey will address as many of your questions as possible, so you can type those questions in at any time during the presentation. Also, there is one continuing education professional development hour that is available for webinar attendees. Please click on the Download Certificate link to the left of the slide area to receive a certificate of completion. Today's event is being recorded and archived at www.achrnews.com. All registered participants will receive an email within 1 to 2 business days that has a link to view a recording of this event. And with that, I'm now very excited to turn this over to today's presenter, so please welcome Trey Austin. Trey, it's all yours.
Thanks, Mike. As you stated, my name is Trey Austin. First, I want to thank Climate Master and the news for allowing me to do this today. I'd like to start off with a brief introduction of ground source heat pump systems. The first thing to note is the topic and discussion is going to focus mostly on vertical borehole systems, mostly because 80% of the projects that are out there in the commercial market represent vertical borehole systems. Certainly there are horizontal systems and pond and lake loop systems, and if we have time here at the end, I will cover briefly a couple of things on those. But otherwise, we're going to stick mostly to vertical borehole systems with regards to the outside part of the projects. It's important to note that there are other design and installation elements that we want to be aware of, and I'm going to cover those as well. And then for those of you who are on that are engineers, one of the things you kind of need to think outside the box just a little bit, myself being an engineer, I can say this, to understand that ground heat exchanger designs and installations have both science and art to them. There is true engineering design that takes place to make sure it's properly sized, but there is some artistic aspects that we have to remember and be flexible to understand that things can happen, and you got to be able to adapt to those types of changes in the field. Drilling conditions may all of a sudden vary and change on you and things of that nature. So please bear with me in mind as we move through this. Some things are going to go through a little bit more quickly than others. Now, as far as the general understanding of ground source heat pump systems, if you're unaware of some of the key benefits you can see on the slide here, the first thing to note is the energy savings component. That's a big reason why our industry is in existence. If you look at a typical building project and understand that we're trying to generically cover a lot of projects across the United States, that when you look at these projects as a whole, we represent about, a typical project will save somewhere between 30 to 70% lower energy costs, which typically translates to about 25 to 45% lower utility costs. Now, again, things that are going to vary that are the actual utility rates in your area, things like natural gas prices, propane prices, heating oil prices, and electricity prices. And even within electricity prices, what are you paying for demand? What are you paying for consumption in the form of kilowatt hours and kW? Those will roll into that, and some people are going to have varying savings on a project just by utility rates alone. Now, we also save dramatically on greenhouse gas emissions. When you look at Energy Star ratings and building ratings that are out there and things like that, will typically be somewhere between 40 to 70% lower in all of your greenhouse gas emissions across the board. Now, depending on your project and depending on how you look at it, when you especially when Energy Star looks at it, they look at it from a site and a source level. And so when you look at it on a site level, because we become an all-electric heating and cooling solution, we do have the capacity to claim 100% site reduction in greenhouse gas emissions. Now, again, if you look at the source side of this, though, we realize that most of the time we're pulling electricity from power generation plants that probably are coal-fired or natural gas-fired. So you got to understand there's a difference between site and source. 100% for site, but when you look at the source and consider that, we're saving typically 40 to 70%. We also have longer lifespans. There's been some studies that have been done over the years that have proven that ground source heat pump systems have a longer lifespan on the equipment. The vertical borehole ground heat exchanger actually has a long life based on the plastic pipe that's out there, and if the engineers designed it correctly, it will last indefinitely, or at least as long as the building will last. We also have greater comfort. Again, there's been a few studies that have been done on that as well to show that ground source heat pump systems or GeoExchange systems provide some of the best comforts. In particularly, there's been some studies in some schools. Within the same school districts, they've evaluated a ground source heat pump school and evaluated a conventional school, and it's shown that testing scores have been higher in the GeoExchange schools. We also have less maintenance and simplified controls. Again, we can take this all the way down to mostly just changing out filters from a maintenance standpoint. Very little that takes place. There's no certifications that need to be required. Most of the equipment maintenance, if something were to go wrong with a unit, can be handled by any normal certified refrigeration technician and things of that nature. Now, as far as control systems go, we can make it as simplified as a single wall-mounted thermostat to as complex as any building automated control system that maybe is trying to be ran over the internet. So depending on your project and depending on the level of sophistication you want with it, we can take the controls aspect anywhere from small, easy operable to complex and logical. As far as aesthetics go, one of the major benefits that we see out there and why some clients will choose these systems is just the appearance of this technology alone. Again, the ground heat exchanger is buried and underneath the ground. You don't see it. It's typically going to be under a parking lot or under a green space area. All of the equipment is brought indoors and is typically hung in ceilings or in crawl spaces or attics or is located in mechanical closets or mechanical rooms. So we are able to remove most of the outdoor air exposed equipment. Now, I will caveat that to one level. We still have to deal with ventilation air, outside air. And when we make those types of considerations, we typically may still have some equipment mounted out there that are dealing with our ventilation or fresh air component of this. So we may not be able to completely eliminate all of the outdoor air equipment. But for 90% of the projects, we can still even work around that and bring in the ventilation equipment indoors as well. And then when you're looking at any LEED or green building type of solution, or like I mentioned earlier, Energy Star rated project, certainly ground source heat pump systems should be one of the top 2, top 3 technologies that should always be considered on that first cut. Now, there could be certainly reasons why we're not past that first cut and move on. Again, utility rates may play into that. Installation costs may potentially play a role in that. There could be numerous factors into that. But certainly on every LEED project, on that first cut level, we should always be evaluated. When you look at LEED projects, and so when LEED was initially going back in the early 2000s, and even now to some extent, when you look at some of the highest LEED-rated projects that are out there in the United States, if you look at those in a lot of detail, you'll know that the mechanical systems on majority of those projects are ground source heat pump systems. In fact, when LEED came up with their system, the very first LEED Platinum certified building in the United States had a ground source heat pump system on it, and that's what helped that building achieve LEED Platinum status. Now, when you look at the long-term viability of these, a lot of times people want to understand what is the economic viability of this project. Does it have a financial payback for me if I invest this additional capital cost to do a ground source heat pump system? And so when we look at our industry and we look at the technology and how it's been performing for various people, you can look at the slide here and see since 2009, when we had a tax credit that was included for our industry. We have 10% commercial and 30% residential. When you look at the installation costs, and typical installation ranges have been between $18 and $22 a square foot, that when you factor in the tax credit and what the operational cost savings are for a ground source heat pump system, typical payback on a system right now is typically between 6 to 10 years, and if you're able to leverage those tax credits even more, you might see paybacks that are somewhere between 2 to 5 years. Again, I've seen those vary all across the United States in a wide range, so don't take it to think that your particular project may itself be a 2-year payback. That may be a very unique situation and very difficult to achieve for some people, but it has. I've been involved in 1 to 2 projects, but 1 to 2 projects out of 30 that I've been working on that has a 2-year payback is certainly nothing I can continue to tout very much. So there is a payback range. It's going to vary for everyone, and you've got to understand a lot of the ins and outs of the installation cost and the utility rates. Now, in addition to those baseline tax rebates that are out there, the 10% flat commercial and the 30% residential, right now in the fall of 2010, President Obama did renew a couple of additional tax credits that you may be able to leverage your project for your owner, or if you're an owner on the call here, that you may be able to consider this. One of those is the 5-year, what they call the Modified Accelerated Cost Recovery System. Basically, it allows you to depreciate the ground source heat pump system and all the equipment involved with that, both inside and outside installation cost. In addition to that, bonus depreciation may be considered. We're almost a little bit too far into 2011 to really look at that, but if you've got a project that's potentially got a ground source heat pump system on it right now currently being installed and is going to be up and running by the end of the year, then you might look at this. But there is 100% bonus depreciation write-off for 2011, and then for 2012 it becomes 50% bonus depreciation write-off. Now, if you look at that website URL address right there, and you go to DesireUSA.org/incentives and then /state and federal, you'll see a bigger breakdown and description of this. And I'm certainly not any tax person, and I would recommend to you that you and your client go to a tax attorney or a CPA or somebody that's familiar with the tax laws. But there are stipulations in there and criteria that an owner has to meet in order to qualify for these 2 additional tax credits. However, the reason why this is important is because we've seen some projects for this year and a couple of projects for next year that do qualify for both the 5-year MACRS and the bonus depreciation tax credits, that when you factor that in addition to the 10% commercial tax credit, they've been able to write off and recover the entire cost of the geothermal heat pump system within 1 to 2 years or less. And that's a dramatic change from where we were at 9 months or a year ago. So if you do have a project right now that you're looking at constructing that would be completed and does have a ground source heat pump system on it for this year, or if next year, you certainly would want to take a look at these 2 criteria and see if your project may qualify for that. Now, as far as understanding the ground source heat pump system, let's start off with what's involved in the inside of the building. Typically, we have a ground source heat pump unit, and we've got varying types of models and configurations that are available on the market from manufacturers. The most common for commercial projects are going to be these first 2 that I show. The first one that you're looking at right now is a horizontal heat pump unit. This typically has a height to it of anywhere between 18 to 20 to 22 inches. Has a width to it also of about 20 to 22 inches. And then the length or the depth of the unit varies depending upon the actual capacity. So for instance, a 2-ton unit may be 30 or 40 inches long, whereas a 4 or 5-ton unit may be 60 or 70 inches long. Now, you might typically see these installed in attic spaces or in crawl spaces, or in most commercial buildings, most people look to hang them above the ceiling lines, beneath the floor structure or beneath the roof structure, but above the acoustical ceiling line. So that's a great way to get those installed above the ceiling line and out of the way. Now, the next most common unit that you'll see installed is what we call a vertical heat pump unit, and obviously it sits upright. The cabinet has virtually the same dimensions. It's about 18 to 22 inches across, has a depth typically of about 18 to 22 inches, sometimes a little bit longer. And then the height of it will vary depending upon the capacity of the unit. Now, a couple of things that I have to note on the vertical units that you always need to be aware of, because people try to put these in closets all the time, is to understand that the return of the heat pump unit is always on the side of the unit, which you can see right here. That return has to be big enough to get all of the airflow across the coil, because that refrigerant coil is right there immediately to the return opening. And so if you're putting this in a closet, you better make sure that you have enough room to get either the return ductwork or have enough open return to get sufficient airflow where the unit will start to trip off. Now, you can get this vertical unit in two configurations, what they call an upflow unit, which is what's shown here. This is where the fan section is mounted in the top part, and the compressor and controls and coaxial heat exchanger coils are all located in the bottom section. So the air is discharged off the top. The second model that's available is what they call a downflow unit. Again, the return is on the side of the unit, but they basically take the compressor section here and move it to the top, and then they take the fan that's here in this section and they move the fan to the bottom, and then the air blows out the bottom. So it's a really nice, unique feature here. If you've got a two-story structure and you've got your mechanical room perhaps on the second floor, and you want to look at putting the heat pumps on the second floor but serving the first floor spaces, so a downflow unit would make perfect sense in that case. Now, the next type of unit that you might see is what they call a console heat pump unit. This is a direct room unit, so you might see these typically in your hotel or motel configurations in the outside wall, or you might see these in spot private offices, things of that nature. I do caution people about using console units, though, in a new construction project. Because they are direct mounted units in the room, they do have a tendency to be a little bit more noisier, because the compressor and all the operation is right there in the room. Now, people who like white noise, it may be a perfect opportunity. The next unit is what they call a rooftop unit. Again, if you run into a situation where you've got no other options to put in a horizontal or vertical system and bring all the equipment indoors, your only option is to put equipment outdoors and on the roof, a rooftop unit might make perfect sense. However, I still would caution using these units. They do have a tendency to be a little bit less efficient on both the heating and cooling side of things because they are mounted outdoors and are exposed to outdoor weather conditions. And so if you're looking at a new construction project, personally, I still try to promote the horizontal or vertical heat pump approach. But if that's not an option and you have no other choice for new construction, a rooftop could fit nicely. Rooftops also have a good marketplace for retrofits. If you've got an existing packaged rooftop unit and you're looking to replace that unit, it's at the end of its life and needs to be replaced, you might consider replacing it with a rooftop ground source heat pump unit. These can handle all sorts of outdoor air temperature conditions. In fact, they can be designed to handle they can be designed to handle 100% outside air type of conditions and situations. That's a little bit more of a customized unit, but it is possible to make those types of units. The next type of heat pump unit that's there is a vertical stack heat pump unit. Again, you might see these in condominiums and apartments where you've got multi-floors. You might see these actually both for ground source applications and water source applications. But these have a tendency to be really small and compact, 20 inches by 20 inches, and then the height of it is typically about 6 foot or so. They can be flush mounted against the wall. I've even seen these used in some classrooms, believe it or not. They can handle a little bit of supply ductwork, although their fans are pretty small, so their static capabilities are pretty limited to around a tenth or a quarter of an inch of static pressure, unlike the other units that can do 3/4 inches or so. But again, they have a great place, and actually from a unit number of units that are sold, this is actually starting to make a pretty big dent versus the horizontal and vertical heat pump units. Now, the next unit that's there is what we call a split heat pump unit, where it's literally just a compressor section, controls, and has the coaxial water connections to the ground loop. And then you've got another set of connections of refrigerant lines that you can then route to any remote air handler or refrigerant coil. You'd see these in a lot of places where maybe you don't have enough space to put in a horizontal or vertical unit as a single packaged unit, and so you need to split the air handling section, if you will, versus the compressor section. So a split unit would make sense there. I've also seen these a lot in retrofits where you've got an existing gas-fired furnace system with a a DXA coil on top of it for air conditioning, and the owner wants to retrofit the furnace out, but would like perhaps to keep the furnace as either backup or supplemental heating. And so what they've done is they've retrofitted the A coil, either replaced it or was converted over, but used the same A coil, tied on a split unit, and still reused the existing furnace fan to circulate the air through the existing zones or the spaces. We actually had a project where we had a retrofit of a historical registered building, and we didn't have enough room for the heat pumps. We couldn't do a lot of demo work to a lot of the walls and ceilings because it was a historical registered facility, or structure, I should say. And so we took all of the heat pump compressor sections and put them downstairs in the old coal-fired storage room where they stored the coal, and ran the refrigerant lines upstairs to all the different remote air handlers that we were able to get located in some small closets and stuff. So they certainly have a place as well in certain places. All right, the final one here is what we call water-to-water heat pump units. They fit a variety of hot water and chilled water applications, and I've got 3 different styles and models that are shown here. The water units, these are typically going to be 20 or 30 or 50-ton water-to-water units, and we'll always have 2 compressors inside of them. And we have large projects where maybe we've got a 200-ton system that's a 200-ton chilled or 200-ton hot water system. We'll bank 3 or 4 or 5 of these units together and then stage the compressors. So we basically create an 8-stage or 10-stage boiler or chiller configuration to supply hot water or chilled water to coils that may be mounted into your traditional air handlers. We're seeing this become very popular with engineers right now because it allows them to stick to their templated VAV systems that they like to design with central air handlers and remote VAV boxes, and then the heat pump here just supplies hot water and chilled water to the main air handlers, and perhaps even sometimes there may be coils on the VAV boxes themselves. So it's becoming more and more popular here recently because engineers find this a little bit easier to swallow, if you will, if they're not familiar with the ground source heat pump technology, that they're a lot easier to adapt to just taking the boiler and chiller out of their existing projects and putting in a bank of water-to-water heat pump units. The next unit here in the middle is what we call a high-temperature hot water unit. This is kind of a specialized unit. One of the things and limitations that water-to-water units have on the hot water heating side is they're limited to about 120-degree hot water. So going back actually to the conventional systems here at the big boy water-to-water units, one of the things that you typically have to do is on your heating coils, instead of typically designing a 2-row heating coil, to maintain the same discharge air temperature with lower water temperatures of 120 degrees rather than a boiler temperature, say, of 160 to 180, you're going to need probably a 4-row or a 6-row heating coil instead with that 120-degree hot water. But assuming that that's not the case, in some small markets where we've got radiant systems or baseboard systems that we want to retrofit, there's this nice little 3-ton water-to-water unit that's capable of making about 140, 145-degree hot water at rated conditions. So it has its unique place. The problem is, though, it's very small in capacity, so it has extremely limited applications, but I've actually used it on 3 projects where that was a great little fit for that situation just because I needed high-temperature hot water, trying to retrofit out an existing baseboard house, and it was a good fit. On the right side here, we've got a standard water-to-water unit that ranges in capacity between 2 to 3 tons up to about 5 to 10 tons. And these have a variety of uses for radiant floor heating systems, domestic hot water heating, things of that nature, or small HVAC systems. You know, if you still want to do your air handler with VAV boxes, if you've got a 5-ton or 10-ton building or something of that nature, these little water units here could work well for that. I've typically used them for radiant floor heating systems, both commercial and residential systems, and I've used them for commercial hot water, domestic hot water heating projects as well. So just wanted to have this slide in here to show, or these slides in here to show people that heat pumps aren't just a single box, that there is a solution, and you may have one project where you may use 4 or 5 different types of models of heat pumps here because of the certain situations of applications you have on a particular project. The nice thing is that you do have this variety of use with the heat pump units. So it's no longer just a single box horizontal heat pump unit. If you need a rooftop unit, you can get it. If you need a vertical stack unit, you can get it. So it's a great little thing to have there. Now, as far as some of the design things that we need to know about designing a ground source heat pump system is we need to know what the building input information, we need to know what's going on out at the ground. We call that the Borefield input information. And we also need to understand, are there any construction constraints here on the project with regards to installation or how the building itself is going to be configured. So let's first start off with understanding some of the terminology on the vertical borehole system. One of the things to note here is the first item, which is in red, indicated by the red arrow, and that's the borehole itself. Typically across the United States, we're going to drill a borehole between 4 1/4 inches in diameter up to about 6 inches in diameter. Now that's going to vary by drilling conditions. It's going to vary by drilling contractors that are out there and their particular rig setup and how they're willing to go. But that's a typical range. One of the things we try to stay away from as an industry is using the terminology of well or well hole or well field. The reason is because in some states, the way the state regulations and jurisdictions go, that if you define something as a well, they interpret it as a water well, and it falls under a category of certain restrictions to do a water well testing or a water well system. Usually a lot more red tape involved. That's the first thing to understand. But if we define this as a Borefield or a borehole or a geothermal borehole or something of that nature, then most states have recognized and have a whole different set of regulations. In a lot of cases, there's a lot less restrictions involved that allow us to proceed a lot more easily. So trust me, though, this is a difficult terminology to get over. So, I mean, I still see well hole, and well field all the time, even from people that are seasoned veterans in our industry. It's just old school, and it's just hard to break, and I understand and get that. But you do want to be careful about the terminology you're using in certain states because it may throw this into a different category. Now, the next thing here that's in green is the pipe itself. The pipe is actually made out of a material that's called high-density polyethylene pipe, or HDPE. It is black in color, but it's the same type of plastic that you see all of the natural gas lines being installed. That typically is yellow pipe. Ours is black pipe. Generally speaking, it has a little bit different pressure classifications on our piping than the gas, so that's why we're black, but also it's just a differentiator. There's purple pipe, there's blue pipe out there. Geothermal pipe is historically black pipe, and we call it HDPE pipe. And there are 3 common pipe sizes that we put down into those vertical boreholes: 3/4 inch, 1 inch, and 1 1/4 inch. Now, what's going to decide partly on whether we're going to use a 3/4 inch loop versus an 1 1/4 inch loop is the diameter of the borehole. So if we're in a particular area and a particular drilling contractor tells us that, well, based on the drilling conditions or his drilling experience in that area, he needs to drill a 6-inch hole, we are likely going to need to choose an 1 1/4 inch pipe. The reason for that is we want to maximize the pipe surface area that's in contact with the ground. All right. In addition to that, we also, which I'm about to get to this one in a second, is the grout. We want to minimize the amount of grout that goes down into the borehole as well. And so there's this kind of optimization procedure that takes place here of understanding of putting in the maximum size pipe we can get in there using the least amount of grout that we can. And the reason for all of that is because when we go through the design of a vertical borehole system, the pipe size, the grout conductivity, the volume of the grout, the spacing between the 2 pipes there that are indicated here in blue and red, that spacing, all of that gets combined into a term that we call borehole thermal resistance. And the objective here is to reduce the borehole thermal resistance. And the best way that we can reduce the borehole thermal resistance is 3 things. Reduce the size of the borehole if we can, which sometimes we're limited on that. We want to maximize the pipe surface area, which means put the biggest amount of pipe that we can in there, and also that also reduces the least amount of grout that we could get in there. But in addition to the grout, which is my next point here, we want to use a grout that has the highest thermal conductivity value itself. Right now, typical grout has thermal conductivity ranges of about 0.43 up to 1.2. Now, as an industry, we did some research back in the 90s to try to figure out was there a way for us to get this borehole thermal resistance value down. Industry standard at that time was using bentonite-based grout, which has a thermal conductivity on its own of about 0.43. Well, what we found out through some of that research and testing is that if we actually mix in high silica sand and increase the total solids content, that by mixing in this high silica sand, we can actually double the thermal conductivity value from 0.43 to 0.88 on the low side. Well, again, that takes the borehole thermal resistance value down, which decreases the amount of bore footage that we need to have on a particular project. So by just changing from standard bentonite grout to what we call thermally enhanced grout actually can save you as much as 20% on the total borehole footage. So if you had a project that was, say, 100,000 linear feet, by just changing the grout that you're using on the project from standard bentonite grout to thermally enhanced grout, we're saying that you're going to go from 100,000 linear feet to 75,000 linear feet alone by itself. So it's important to understand that we want to do that as quickly as we can. Now, you can take this value even higher up to about 1.2, but there are going to be more physical construction constraints that fall into place here. Grout with a thermal conductivity of 1.2 has so much sand in it, it becomes very, very difficult to pump in a grout pump. And if that contractor's not set up for that, that grout will actually get stuck in all his grout piping and grout setup, and actually it won't solidify, but it will also become, he has to break down all his equipment and wash it all out. I have a lot of contractors out there that tell me that if it's thermally enhanced beyond 0.88 or 0.95, they won't even bid on the project because they don't have the equipment and the capacity to handle the higher thermal conductivity grout. So you want to be careful about whether you're going to use what I call ultra thermal conductivity grout here of a 1.2 value, or whether you can live with the 0.88 to 0.95 type of ranges. Very critical for that. But the goal here is to understand we want to get all of this water temperature in here to move energy between that fluid and that pipe and get it to the ground itself. And that next dominant characteristic is the ground thermal conductivity value. That's an important characteristic that we're going to get to here in a minute of how we obtain that. One of the things I like to explain to people about how a ground heat exchanger works is understand it as a thermal battery. And this thermal battery has a starting point here of energy in it, and that energy comes from two primary locations. First of all, part of it comes from the sun. About 45% of the sun's energy on the surface here is absorbed by the ground. The other is, obviously, we've got this passive geothermal gradient here of energy that's coming from the fusion heat of the earth, if you will. And so from about 0 to 600 feet deep, we have this nice little steady state band of energy, all right, that's available to us to take advantage of. And our thermal battery here is going to discharge itself or recharge itself. So in the wintertime, when we're actually trying to heat a building, our thermal battery is discharging the energy. It's taking the energy from the ground and moving it to the building. The heat pump equipment in the building is then taking that energy, manipulating it, and delivering that hot air to the space or that hot water to the heating coils. In the wintertime, we're actually recharging that thermal battery. We're taking heat out of the building, it's putting it into the fluid that's circulating to the pipe that's in the ground, and then the ground is absorbing that heat. Now, depending on where you're at, depending on what type of building is and the application, this thermal battery here is going to recharge and discharge itself over time, and there may be an imbalance depending on where you're at. Historically speaking, in the south, you're going to be cooling-dominated buildings. Historically, in the north, you're probably going to be balanced, or you're going to be slightly heating-dominated buildings, especially when you factor in ventilation here. So you got to understand how imbalanced are we, how far out of whack are we. But we can still account for that correctly in the Borefield ground heat exchanger design itself. But it's understanding that this is a thermal battery that's recharging and discharging. It's an important concept to understand. So from the building side, there are two key critical components that we need to understand, and this is where we differentiate from conventional systems. Not only do we need to know what the peak BTU per hour heating or cooling load is for a space, we also need to understand what we call the cumulative effect, or the raw BTUs, over a given period of time. So we need to understand, and people will tell you we need this on a monthly basis, January, February, March, April, May, June, July, and so forth. But it's understanding that this accumulation or this cumulative effect carries through the ground heat exchanger design. I can't design a ground heat exchanger by just knowing the peak BTU per hour load only. I have to understand the cumulative. And here's how we understand the cumulative. If we have a 20,000 square foot building and it's an office building, yeah, it may have a 40-ton peak BTU per hour heating load. But it's an office building. What if I take the same building, the same square footage, and it's still 40 tons of peak BTU per hour, but instead of an office building, I tell you it's a school. Well, that load profile difference is going to affect the cumulative effect of BTUs this thing needs to provide over a given month or a given period of year. So even though I've got an identical building that may have an identical peak BTU per hour heating or cooling load, if I don't understand the cumulative effect and how that building's being used, I'm going to miss the mark on my Borefield design. And it'll either be under-designed or it'll be over-designed. So you're either going to spend more money than you needed to if it's over-designed, or you're going to be in a lot of trouble if it's under-designed because you're not going to have systems performing right. So it's critical to understand not just one, but both of those components on the inside the building. All right? So here's a simpler pictorial way to look at it. Design loads, which is your BTU per hour, versus the energy loads, which is our BTUs, both have to carry through in order to right-size our ground heat exchanger. Now, so here's some of the common programs that are out there that can do this. eQuest, Trace 700, HAP, and I believe Right Suite has that capability. There certainly may be a couple others. These are just to highlight a couple of what those are on the market that can do that. I cannot take, typically speaking, a residential program and design a commercial ground heat exchanger. That's an important thing to understand. Now, on the Borefield, here's a couple of things to know on the inputs. We need to know what is the minimum and maximum water temperature that we're designing to. That's also going to translate to what are the COP and the EERs of the equipment. So typical limits, and this is going to vary across the United States, are going to be 145. Honestly, that's just a suggested starting point. You should always look at every project and decide from there, based on iterations, whether or not you need to massage and relax those limits or constrain those limits some more to balance the size of the bore field, which is going to be related to the installation cost, and also balance the COP and EER of it. My own personal experience, I live here in Denver, Colorado. The majority of my projects here, my points that I start out with are 95 and 35. And I go from there. I've got some projects where I'll take it to 100 or 105, and I've got some projects where I'll take the low limit from 35 and maybe I'll raise it to 40 or maybe lower it to 30. But for me in my area where I start out on my projects, it's 35, 95. And then understand that we need to, the last point here, understand we need to decide how deep we're going to go on the borehole system. Typical depths across the United States for a project are going to be 300, 350 feet up to about 420 is a typical range. I've seen projects where we go to 200-foot boreholes per depth. We'll also have projects where I've seen 500 to 550-foot per hole on the depths. So you do certainly have those types of very wide extremes, but if you look at the bulk of projects that are out there, 350 to 450 feet deep is an average. Now, how do we get the ground heat exchanger information out there? We want to know ground temperature, ground thermal diffusivity, and then the secondary on some design programs, what we call the thermal diffusivity. Well, those are obviously unknowns to us, and even if we use tables, graphs, or charts, it's still kind of a relative sense. It's not necessarily concrete or absolute. So as an industry, again, back in the 90s, we came up with a procedure that's called a thermal conductivity test. This test will allow us to get these parameters, but the test costs money. Typically, I've seen low-end costs of $8,000 and high-end costs up to about $16,000. It's going to vary depending on where you're at. It's going to depend on how deep your test borehole is. It's going to vary on if you're going to require just standard bentonite ground or thermally enhanced ground on the test borehole, and if you're going to try to reuse that borehole, which you can, on the design of the project, then you're probably going to do it with thermally enhanced ground. Well, all those types of things fluctuate that cost of the test itself. But the reason you want to do this test is because, again, getting these pieces of information will further reduce the conservativeness of what engineers typically do, and it results in a 15 to 25% lower installation cost because we got more, better refined data. For me as the designer, if I were to do a project and I don't have TC test data information, I'm going to be conservative. I'm going to guess a lower thermal conductivity, a lower or higher ground temperature, something that gives me a bigger ground heat exchanger because I want this thing to work. I don't want it to fail. But if I have this TC test data information, then I'm going to be more refined and better off. So what does this test look like? Well, the first thing you're going to do is you're going to hire a contractor to come out on site, and he's going to figure out where this test hole is going to go, or you're going to help him figure out where this test borehole is going to go. Once you figure that up, he's going to set his little rig up here, and he's going to drill that test hole to the specified depth that you're going to do. Now, it's key to know that whatever depth you specify for this TC test is generally going to have to carry through the duration of the project. So if you specify a 300-foot test borehole, then that means the rest of the Borefield is probably going to have to be designed for 300-foot depths. Now, there could be some variations as to why you might need to change that, but if you're going to use these TC test results here for ground thermal conductivity and ground temperature, you better be careful about if you change the depth of the design moving forward. Certainly, you don't want to take a 300-foot test borehole data information and then design a 250-foot borehole system because that is going to put you in a lot of trouble. This is what the test looks like. It's just a box. You've got a portable power generator, and in the end, what you're doing is you're collecting data on a heat pulse on a single borehole, and this is kind of a sample report, which is probably a little difficult to see everything that's on here. But basically, we have a mathematical equation that's taking place behind the scenes. It's called the Eskilson line source. And we found that if we take the natural log of time versus temperature data, it equates to a straight line, which is over here on this graph to the right side. And if you take the average temperature in and out, all right, which is this purple line here in the middle, that the slope of that line actually is the thermal conductivity. So that's the first primary number we're after. The other primary number we were after was the ground temperature. Well, when we do a TC test, if you look at the bottom left graph over here, when we initially, because this borehole is going to rest for about 3 days after drilling, that the water that's inside that pipe is actually acclimated to the ground temperature. So when we first start up the test, we do get the ground temperature on the initial data. So in this case here, it's about 60 degrees, and then the ground thermal conductivity back over here, that slope of that line is calculated right here, which is a little difficult to see, but it's about a 1.24 for this particular project. All right, so once that's done, you can kind of carry that information forward, all right, and once that's done, we've got the information we need to have to carry forward to the Borefield design. Now, as far as installation information, what you should be aware of, well, externally, all that pipe, the high-density polyethylene pipe, it's all heat fused in the ground. There are no joints out there that are soldered or fused together, that are soldered or welded together or have pipe threads on it. We actually heat that pipe up to its melting point, push it together in a butt fusion process, which is the most common one, all right? And once that pipe cools down at that joint actually becomes stronger than the pipe itself. There are also electrofusion joints and socket fusion joints are going to be the other common ones that you'll see that are in the field out there. Electrofusion has a tendency to be pretty expensive, so I've only seen that mostly in situations where they're trying to do a quick change out in the field. Somebody accidentally cut the pipelines and they're out there digging a small trench trying to make a patch repair or something like that. Or in extreme cold temperatures where the heating irons just can't maintain temperature because the ambient air temperature is way too cold outside, so they may switch over to use electrofusion joints instead. As far as the pressure tested, most of the time if you're looking at doing an air pressure test, most people run it to about 100 psi of pressure. That's not very safe, quite honestly, because compressed air at 100 psi has a tremendous amount of energy built into it. So if there were to be a leak and a guy happened to be real close by, that could be pretty nasty. Generally speaking, the industry recommends that you do hydrostatic or water pressure testing to about 40 psi. It's actually a lot safer because if that pressure to be released, it actually would dissipate very quickly and wouldn't hurt anybody if they were close by. But there are situations where guys like to run 100 psi air pressure, and that's their prerogative. Just generally speaking, it's not the best practice here. As far as antifreeze solutions go out there, when do you use that? Well, I would say anytime you're designing a system where you're entering water temperature or your loop fill temperature would be 40 degrees or less. Typical average mix ratios are somewhere between 10, 20, or 30% ranges. And there are 3 common types of antifreeze solutions that people use. Propylene glycol, which is food-grade glycol, safe to handle. Methanol, which has a little bit more flammability concerns, as well as ethanol, can also be used. They all have their trade-offs. Propylene glycol has bigger pumping penalties. The colder it gets, the higher the viscosity becomes, but is very safe to handle and non-toxic for human consumption. Methanol and ethanol, they have high flammability, but when they're mixed with water, I think they're pretty safe to handle. they do have less pumping issues than the propylene glycol. So across the U.S., I've seen a mix of these three, but the dominant one is probably propylene glycol. But I will also say over the last couple of years, propylene glycol is starting to become very, very expensive per gallon. So we've seen some projects where there's been some change orders requested to switch over to ethanol or methanol just to reduce it. I think we're talking on the order of propylene glycol right now is between like $11, $12 a gallon versus methanol or ethanol. That's at $4 to $5 a gallon. So on some projects where you're using 1,000 or 2,000 gallons of glycol, that's a pretty big cost difference. All right, and then lastly here, before we get into some pictures, is the grout itself. We've talked about that earlier on using thermally enhanced grout versus your standard bentonite grout. Our standard practice for me personally is always use thermally enhanced grout. The only time I've allowed bentonite grout is in winter conditions here in the mountains of Colorado, where it's a little bit harder for them to have to work with that. For me, that's the only exception. Otherwise, it's our standard practice to always go thermally enhanced grout. But if you do have grout, anytime any of it needs to be mixed up, it's important to know that during the installation to try to take periodic samples and send that to an independent laboratory for testing to make sure that the thermal conductivity that you specified for the grout is being met by the contractor. That's a pretty simple thing to do. You also want to make sure that you see the guys grouting the boreholes from the bottom all the way up to the top. We never want to grout a borehole from the top down to the bottom because it might bridge itself and would create gaps or pockets in there. And then finally, tracer wire or metallic tape is always suggested to proper locate this stuff in the future, or if anybody else needs to do other underground utilities and needed to do locates. And then proper balanced headers. We want to make sure that if we've got 10 circuits that they're all supposed to supply 80 gallons per minute to each set of boreholes that are on there, that they're doing that, and we do that with properly balanced headers. Maybe you can achieve that with just some standard ball valves or butterfly valves to adjust the flow, or you maybe even want to put actual balancing valves on there where you can truly measure an accurate flow rate and then make an adjustment to achieve your desired flows. It's important to know, especially on larger commercial systems. Now, as we go through some of the installations here, just wanted to cover that here real quickly. This is a mud rotary drill rig. This is a guy where he's shoveling the cuttings out of the back of the rig. It has a tendency to be a little bit more messy than, say, a drilling contractor that's got what we call a mud puppy. Mud puppy is just a shaker table here. You see here the site's all nice and dry, and his mud pit box here is a lot smaller and a lot cleaner. He's about to load a loop here in a hole. But all the fluid and cuttings are going over here to this little shaker table here. Again, it's a mud puppy. And in these little piles, they're separating the drill cuttings out from the drilling fluid. So not only are they able to keep the site a lot cleaner, they're actually using significantly less water on a particular project here. This pile here represents about 8 boreholes that have been drilled 400 feet deep so far. But not all contractors have that, and it's not necessary, but certainly is an important thing. Now here's a picture of that HDPE plastic pipe that typically goes in the ground. Right now you're looking at what we call a 1-inch circuit. Now if I were an engineer or a designer and I was walking into the field to find out if the contractor is using the right pipe and everything, I would take a look at this writing here that's on the pipe, and I would get a gauge from that to know exactly. There are 3 common things I'm looking for here. One of them is the pipe size. One of them is the DR rating, which we want it to be a DR 11 or better going down into the boreholes. And then we also want to make sure that it's the right PE cell classification number. That says 3408 there. Recently here, the industry standards are changing their number sequencing, and also I think now it's 4710. So you may see 3408 or 4710 in the field, and either one is fine. Excuse me. And then, we talked a few moments ago about butt fusion. This is a perfect classic picture of a perfect butt fusion joint here. They've had the heating iron here in the middle. They've heated up those 2 surfaces of pipe, and then this contraption here has pushed those 2 pipes together to create a butt fused joint. And like I said, once that joint, if it's properly been done, it cools off, it actually becomes stronger than the pipe itself. And that's been proven time after time in tensile tests. It's another picture here of an installation. That's another mud box here in the back. They're about to load a U-bend loop in here for a particular project. Once all the holes have been drilled on a given project, you're going to see them start digging trenches like this with all the little tails of all the boreholes sticking out. They're about to connect all the lateral lines together. We typically call that headering or header lines. So they're going to connect all those together in pairs of 1.25" or 2" or 3" pipe sizes. This is one where the header line's already been laid down in the trench. The borehole lines have been cut off and connected into the circuits. That's a little bit difficult to see. Let's zoom into this picture here. So this is the top of a borehole, and this is what it would look like if they snip off the pairs and connect it to both the supply and return lines. These are 90-degree socket-fused elbow fittings that are on there. This is one way to connect the lines to the supply and return. Another way is that you can actually take the pipe coming out of the ground and bend it over and make the connection straight into the T without the need of this 90-degree elbow joint. The problem with that, though, is the contractor has got to relieve the edge here of that borehole, because if he risks bending that pipe over, he might kink the pipe as he bends it over if he doesn't put relief on that lip there. So it just comes down to contractor preference or even designer preference. Again, our standard practice in our office is our details and our specs require that they do the 90-degree fittings. To me, it looks a little cleaner and is a lot easier to see that it's done correctly. To rely on them to make sure they taper back this edge of this lip here and bend the pipe over and not kink it just seems like there's just a little bit more level of risk there, but certainly is acceptable. Here's another installation here where they over-excavated the site. So right now they're drilling all the holes at 5 feet below grade. They had really terrible soils here for the parking structure, so they over-exed the site. Saved a lot of money here without having to do all this additional trenching, as you saw in the previous couple of pictures. So they're drilling all the holes now, and then they'll come in and header all these lateral lines at this depth, and then they'll backfill with all this dirt back here in the back that's currently being treated. So it was actually a nice little cost-saving measure for the project. This is another side view here of that same project. So you can see they over-exed the site here about 6 feet, 5 feet or so. They've got a mud puppy, so all these, you got your tail cutting piles here, and then you got the loop loaded in the hole right next to it. So that's typically what a vertical loop field looks like. Now, if you do run into a project where you've got ability to do horizontal systems, here are some constraints you want to be aware of. Typical depths need to be 6 to 12 feet. It can be cheaper on its installation cost, but the thing to understand is that first point is that typically a horizontal system will take up 3 times the site surface area as a vertical footprint. So for every 1 acre that a vertical borehole system takes up as a footprint, realize that a horizontal system will need 3 acres to provide the same equivalent performance as a vertical system. So the reason we don't see a lot of projects here is because a lot of office buildings, a lot of commercial sites just don't have that much available land to it. Where we might see commercial horizontal systems being utilized would be state schools, state buildings, things of that nature, where there's usually a lot of green open space around it. Again, going back to school, you've got parking lots, you've got athletic fields, and then you also have green spaces. So you'll see a lot of schools looking at horizontal systems as a cost-saving measure. But realize, obviously, that in the commercial world, if you're looking at retailers or other office buildings and things, we just don't have that afforded space area to deal with that. There are a couple of pictures of what horizontal systems look like here as we end and close this. This is a big 800-ton horizontal system being installed. This was such an excavation that this particular contractor actually ran 3 scraping machines constantly for about 4 days straight to excavate all this area that was needed to put in 100 loops. And you can't tell it here, but off to the right, this goes off about another 300 or 400 feet. So really massive, big horizontal system. Here's another one here where it's going to go inside of a pond or underneath a pond. So they're laying out all the circuits right now, and then once that's completed, this is kind of the after picture where the pond is filled up. So, again, you don't know anything's out there once things are completed in there. Now, if you do a horizontal system, things to be aware of as far as terminology go here, let me get to that last picture, is understanding the definition. First, we have the length, all right? So the length of a circuit could be anywhere between 100 to 150 feet on average. That is a different term than feet of pipe. So based on the pipe being coiled here, you may actually have 1,000 feet of pipe and 150-foot length of distance. So that is going to be critical. Are you talking length or are you talking feet of pipe when you say a number on a horizontal system? I got an 800-foot horizontal system. Well, is that 800 length or 800 feet of pipe? Understand, too, that the pitch is a critical factor. All right, that's the spacing between the start of one loop and the start of the next loop. Typical pitches are going to be 18 to 24 inches. I've seen sometimes as little as 12 inches, but that's pretty tight. And then the diameter, it's what is the diameter of the pipe as it's being coiled. And again, typically it's 2 feet or 3 feet. And then the spacing is the center from one coil to the center of the next coil. So if you're looking at designs or you're looking at installations and you're using the terminologies here, this is what it is. So with that, we'll conclude our discussion. It's a lot of information to cover in a very short period of time. We're condensing down in 1 hour or 45 minutes here what normally can take 3 or 4 days to discuss. So I hope you guys got a really good high-level understanding and view of what this is about. Right now, I'll turn this over to Mike.
Trey, thanks very much for all the information. We do have a lot of questions. We certainly won't be able to get to every one of them, but we'll start right away. First question from Tom Swanson at Agile Geothermal. His question, he says, petroleum engineers often state that the least expensive drilling is at the bottom of the borehole, in other words, deepening a well. How do you optimize your borehole depths? And I'm assuming that it's not necessarily by trying to keep up with the petroleum engineers.
No. Well, there are practical limitations on how deep we can go. I've been told by the pipe manufacturers that the warranty that's on the pipe, which is typically 50 years, is voided after you go down 600 feet deep. And it's because you go deeper than that, and the pressures that are exerted on the pipe down that depth, there's no guarantee that it'll not collapse on itself. So from a practical standpoint, really the ultimate depth is about 600 feet. Certainly you could try to go deeper than that, but I'd be careful. As far as what I've been told by drilling contractors in this industry is they would rather drill fewer and deeper boreholes. It takes less time for them to set up and take down to move from hole to hole, which in turn saves them labor and cost, which should in turn save the owner money because the bid prices would be a lot lower. Now, I'm not saying it's going to be a 20% or 30% savings, but, you know, a contractor who may bid $12 a foot on a project, if he can do deeper holes, he may bid $11 or $11.50. You know, and then that's nothing nothing to not look at. That's definitely good savings.
Let's see, another question coming in. A lot of compliments coming in here, too. People telling you did a great job, so you must be covering some good information. Here's one. If I have a bunch of R22 heat pump systems, how can I replace them with newer R410A units?
You know, that's a good point. We're seeing a lot of existing water source heat pump projects that are 20 or 30 years old, or even some ground source heat pump projects that are 20 or 30 years old, and the owners are, one, wanting to update with more energy-efficient equipment, or better, I should say, energy-efficient equipment, and at the same time wondering, well, you know, this new 410A stuff usually doesn't result in bigger heat pump units, and how's that going to fit? There are manufacturers, including Climate Master, is a big one, that makes heat pump cabinets that fit their old R22 footprints. And so I think it's worth visiting to say, for Climate Master, I think it's their TC or TRC lines. It is a 410A heat pump unit that is made to fit in the old R22 cabinet sizes and dimensions. And so it should just be literally a one-for-one replacement. A lot of the return and supply openings are also the same.
Okay. Let me see. One of the next questions, interesting one from a guy at Buffalo University. What is the typical compaction level of soils for different horizontal systems? Is there any way you can address that kind of in a generic sense? I know you can't address all the entire country in one answer.
See, you're supposed to clear those for me and not set me up here. You know, compaction requirements for horizontal systems are going to vary dramatically depending upon what is going on top of the horizontal system. Some would argue that if it's an athletic field or green space, that the compaction requirements are just, you know, you backfill and it just naturally settles. Now, some contractors will still use compaction machines, but it doesn't have to meet doesn't have to meet 95% compaction levels. However, if a horizontal system is going underneath a parking lot, or even in some cases, we've done it a couple of times, and I've seen other projects where you go directly underneath the building, then certainly you want to make sure that you do proper compaction back to usually 95%. I will tell you that from my own experience, a lot of times on the compaction, that if they're using good compactors, especially vibrating compactors, and they do compaction tests in lifts, so in other words, they'll lay down a foot or two and then do compaction and then have that tested and then lay down the next lift and all that, that 9 times out of 10, they actually recompact the ground back better than what it was before. so much so that they're actually able to take the cuttings from all of the boreholes and mix that in with the trench cuttings, and therefore all the cuttings from the boreholes don't need to be hauled off. They're mixed back in on the site, and the contractor doesn't have to pay more money to bring in additional fill material. So they work out really well. Now, I know you just asked about a horizontal system. So if you did a horizontal system and your compaction starts becoming better than what it was before, you certainly would have to bring in fill material to make up that difference.
Okay. A lot of questions on the boreholes. Some people asking how long do they last? How long will a loop last? Another one asks, what if I have to dig up one of the boreholes because it leaks? So maybe you could address that a little more.
All right. So there's couple questions that are embedded in that. And by the way, I personally can stay on as long as we need to for a few more minutes anyway. We certainly don't want to go on forever here, but we'll take a few more questions. So we'll run over maybe 5 minutes or so. The longevity, first the pipe itself has a manufacturer's warranty of 50 years. I mentioned that a few moments ago. It has a theoretical lifespan of about 250 years. So it will generally outlast the building itself. And in fact, we've seen some cases where it becomes a residual value to the owner. For instance, like a chain, like a restaurant, say McDonald's, and there are a few ground source heat pump McDonald's where they rebuild those buildings about every 10 to 15 years. They scrape the building and start new. Well, if they have a ground source heat pump system on it, they pay for the ground heat exchanger the first time on the first build. When they're ready to rebuild the building at 15 years, the ground heat exchanger, assuming it's been designed and installed correctly and is still working properly, can be reused in connection back to the next building, assuming that the next building is close to the same square footage, to the same peak load and cumulative load profile. So it really becomes a benefit to the owner to have that residual value that could carry over to a new build. Now, as far as the contractors and if you've got leaks, that becomes a quality control issue from day one. As long as everything gets properly tested, and we showed those air tests and hydrostatic pressure test ratings, as long as all those connections get tested before they get backfilled and they're able to be inspected and recorded and all that, the likelihood of one of those fusion joints leaking down the road is very, very small, and I would say less than 3 to 5% of the time. I mean, out of the projects, I've been involved in the industry for 14 years, hundreds of projects, and I will tell you I've got maybe 2 projects that I had a leak on that the contractor made a bad connection. If there's anything that's happened, usually it's another subcontractor has come through and cut the lines and didn't tell anybody until after the fact or whatever. And so they've had to come in and repair the lines. But it's no fault to the installation contractor for the loop field. It's the electrical contractor or civil contractor or somebody else like that.
Well, here's an unusual question here, Ray. Oh, okay. I'm sorry. Go ahead.
Well, as I say, as far as leaks on the boreholes, those also are very slim. If there's a leak, it's a workmanship issue on the lateral connection lines that are that 4 to 6 foot below grade. The vertical borehole pipe that goes down the hole and back up is all one continuous pipe. There is a fitting that's at the bottom of the borehole. We call that a U-bend fitting. It's typically fused on at the factory, and it's pressure tested there before it leaves, and then it's usually pressure tested by the drilling contractor in the field before they install that loop, and then they usually keep that under pressure as they're installing it into the hole. So as long as that's holding pressure the whole time, there is no other way for that thing to really leak, if you will. The leak is going to occur at the headering line connections at the top of the boreholes that are in those lateral lines that are going to be 4 to 6 feet deep.
Okay. It's kind of an unusual question. It says, can a concrete truck roll over a vertical loop? And maybe you could address that in the sense of what type of maintenance is required for vertical loops, and is there any care that does need to be taken with regard to, maybe heavy weights or anything in the ground that surrounds them?
As long as that pipe has been buried, 2, 3, 4, 5 feet below grade, you can build and construct anything you want on top of that and roll any type of machinery or equipment on top of that. Now, if you're talking about a direct impact of rolling equipment, such as those machines, directly on the pipe, if it's sitting on top of the borehole or something and hasn't been headed or anything, certainly that will, that typically elongates or outshapes, out around, I should say, the pipe itself, and you typically have to cut that off and fuse on a piece to deal with that. But as far as if it's been headed and buried underneath the ground, it doesn't collapse on itself if you roll over equipment or things on it. It certainly would if it were directly rolled on it.
Trey, one more question here. This is probably going to be the final one before we sign off. What happens if I can't complete a TC test prior to the construction start of the Borefield?
Yeah, that's never happened, right? There are a couple of different things that you can do for that. The first thing is you could talk to the owner and talk to the contractor and have them or have someone or yourself come in and test the first borehole that they drill and install, because generally speaking, they're drilling 30, 40, 50, 100 holes or more on a project. That's going to take some time. So if you can test the first borehole that they drill, you can then get those results and go back to your initial design model and update those temperatures and thermal conductivity values in the design model and refine it and decide, okay, are we undersized or are we oversized, and usually make an adjustment. We've had several projects where we've had to do that on ourselves just because we were brought in late to the game and the owner was ready to start construction and said, okay, well, now I want to do ground source, and there's not enough time to let us do all of this procedural stuff. So they said, well, we know we at least need to do about 40 holes. Let's get them going drilling. Let's get the design going at the same time, and then do a test on the first hole. And then usually the contractor has a renegotiation or change order that he's going to set up here on a bid price. He's given an add deduct price per foot or price per hole in his contract so that they know that, okay, we got 40 holes that he's basing his bid on, and we may add as many as 10 more holes or deduct as little as 10 more holes. So he's given us an additional price to be able to make that construction cost adjustment on the project. But you certainly can make those types of changes after the fact and after you get going. And it has happened, that's for sure. And I've even had to do that myself on about 10, 20 projects or so.
Okay. Hey, well, Trey, thank you very much for a great presentation. This does conclude today's webinar for our audience, and please join me in thanking our presenter, Trey Austin, as well as our sponsor, Climate Master.